ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
To continue with our discussion about the basic planes in a crystal lattice, you have seen that we have identified a few planes in the crystal lattice. These are 1 0 0, 1 1 0 and 1 1 1. So, here you can view them more clearly. Okay. See this plane A, B, C, D. This is actually this black hatched plane. This is actually belonging to the family of 1 0 0 plane. What do I mean by belonging to the family of 1 0 0 planes? I mean that it makes an intercept only on one axis and is parallel to the other two axes. In this particular case, it is parallel to x and y axis and it is making an intercept on the z axis. Similarly, if you look at this plane, the violet hatched plane, that is ACHF. This plane is belonging to a family of 1 1 0 planes. ACHF. This is belonging to a family of 1 1 0 planes. And if you look at the triangular plane CEH, this is actually an 1 1 1 plane, that is it makes intercepts on all the three axes, equal intercepts 1 1 1. So, these are the basic three crystal planes about which we need to concern ourselves when we are discussing silicon as a single crystal material, because these are the three planes you will encounter most often and the properties of these planes will be different. Now, why do I say that the properties of these planes will be different? Look at this. Here I have actually taken just this plane ABCD and put it here along with its atomic configuration. If you also look at this model here, this is a plane belonging to the family of a 1 0 0, this plane, right. And what do you see? You see one corner atom here, one corner atom here, one corner atom here, one corner atom here and the face centered atom here. But they are not uniquely contained in this plane. What do I mean by that? What I mean is simply this. Let us consider the 1 0 0 plane. I have a corner atom here and a corner atom here and a corner atom here and one here and one at the center. Now, you can think of so many 1 0 0 planes, right. I have drawn 4 1 0 0 planes here and you can see that this atom is shared by all 4 of them. Now, since there is nothing to distinguish between this corner atom and this corner atom, it implies that all the corner atoms are shared by 4 of the 1 0 0 planes, right. So, the contribution of these corner atoms to the 1 0 0 plane, to one particular 1 0 0 plane is going to be 1/4. And since I have 4 such corner atoms, the total contribution is going to be 4 into 1/4. This is the contribution of the corner atoms. What about the center atom? This is uniquely contained in one 1 0 0 plane. It cannot be shared by other 1 0 0 planes. Therefore, its contribution to the 1 0 0 plane is unity, it is 1. So, for the face centered atom, in other words, the total contribution of the atoms to this 1 0 0 plane is simply 2, right. What is the plane area now? You know that in this lattice we said that each side of the cube is A. Therefore, the area of 1 0 0 plane is A square. So, the density of atoms in this 1 0 0 plane is two atoms in A square area. Therefore, the packing density of 1 0 0 plane is 2 by A square. Let us now think about the 1 1 0 plane. You can also see it here. This is the 1 1 0 plane. In fact, it might be clearer if you look at this, look at the model. This is my 1 1 0 plane. If I draw a big diagonal here, then this is my 1 1 0 plane. Let me try to look at it here. This is this big diagonal and this is the side of the crystal. Okay. Now, I have a corner atom here, a corner atom here, a corner atom here, a corner atom here, and I have the face centered atoms here. These are these two atoms actually, this one and the one at below, right. These two atoms, what I mean is this and this. And in addition to that, I also have the two atoms from the second sublattice sitting on the plane, 1/4, 3/4, 3/4 and 3/4, 1/4, 3/4, right. So, what about the atomic contribution? Again as before, if I try to extend it, you can see each corner atom is shared by 4 1 1 0 planes. Therefore, the contribution of the corner atoms is 4 into 1/4, that is 1. What about the face centered atom? This is one of the face centered atom and it is shared by 2 planes. Therefore, the contribution is half, and since I have 2 such face centered atoms, it is 2 into half equal to 1. In addition, I have 2 atoms of the second sublattice which is uniquely sitting on this 110 plane. It is not shared by any other 110 planes. Therefore, the contribution is going to be unity for each one of them, and for 2 such second sublattice atom I have therefore, the total atomic contribution to the 110 plane is 4. And what about the area of this 110 plane? You know, this side is actually A and this is root 2A. Therefore, the area is root 2A square. Therefore, the density is going to be 4 by root 2A square, which is equal to 2 root 2 by A square. Am I correct? So, you see, for 100 plane the atomic density was 2 by A square. For 110 the atomic density is 2 root 2 by A square. Therefore, atomic density is larger in case of 110 planes. Right. Now, let us take the case of 111. This is the 111 plane, as you can also see here. This plane ECH. Where are the atoms located? At the 3 corners. These are the 3 corner atoms and the 3 face centered atoms, right. You can also look in here. It is going through this diagonal and through the base diagonal. So, you see this corner atom and this corner atom, and in the middle there is a face centered atom at the bottom here. Similarly, on this diagonal there is this corner atom and this face centered atom here. Okay. So, again let us look at the atomic contribution to this particular plane. These are all the possible 111 planes passing through this point. That is, I have 1, 2, 3, 4, 5, 6 planes. It is a hexagon, it has to be, right, because this is actually an isosceles, an equilateral triangle, each triangle having 60 degrees. So, I have 6 such triangles basically. Okay. So, for each corner atom it is shared by 6 111 planes. Therefore, the contribution to one particular there are 3 such corner atoms, each is shared by 6 cells. Therefore, the total contribution of these corner atoms is 3 into 1 by 6, that is half. What about the face centered? Half, it is shared by 2 planes. Therefore, the sum is 2 again. What about the area of this 1 1 1 plane? As you know, this is an equilateral triangle. The area of the triangle can be given by half base into altitude. Therefore, let us do a little bit of high school geometry. I have this equilateral triangle, its side let us call it x. I drop an altitude from here, this is h. Since this is an equilateral triangle, this is going to be actually x by 2 and this is x. Therefore, h is root 3 by 2 x. Therefore, the area of this triangle will be given by root 3 by 4 a square, that is the area, right, because x is actually root 2 a. I think I will just redo this once again, maybe this step should be worked out. So, I have half base is actually my x into root 3 by 2 x. So, I have root 3 by 4, area is actually root 3 by 4 x square, and since my x is actually twice x is root 2 a, therefore, area is root 3 by 4 into 2 a square. So, root 3 by 2 a square. Okay. So, you see the density of atoms therefore, is going to be 2 into 2 by root 3 a square, that is 4 by root 3 a square. So, we have calculated the packing density of the 3 most important planes for our purpose, that is 1 0 0, 1 1 0 and 1 1 1, and you have seen that the packing density in 1 0 0 plane is 2 by a square, packing density in 1 1 0 plane is 2 root 2 by a square, and packing density in 1 1 1 plane is 4 by root 3 a square. Why am I harping on this packing density? Because the packing density controls certain important properties of the particular planes. Okay? So, let us note this point that the packing density in 1 0 0 plane is the lowest. It is the lowest. We will look at some of the other properties of these planes, and then we will try to correlate how the material properties are governed by these atomic configurations in the planes. You can see here some of the basic geometric considerations of the planar structure. First of all, see that when I have two planes are meeting, the angle between the two planes, if I call this angle theta, theta between two planes u1 v1 w1, by u v w actually I mean the Miller indices. Okay, so, it can be 1 0 0, 1 1 1 etc. So, between these two planes u1 v1 w1 and u2 v2 w2 is given by this relationship, cos theta equal to u1 u2 plus v1 v2 plus w1 w2 divided by square root of u1 square plus v1 square plus w1 square multiplied by u2 square plus v2 square plus w2 square. Also, these planes will intersect at a line. The line direction is given by u v w, where u is v1 into w2 minus v2 into w1, v is w1 into u2 minus w2 into u1, and w is u1 v2 minus u2 v1. This is the line of intersection between two planes. And finally, the separation between two adjacent parallel planes, that is, when I say two adjacent parallel planes, what I mean is, you see, this is one plane, okay. This is its adjacent parallel plane, the front plane and the back plane, or you can say this and this, or the top and the bottom. This is what I mean by two adjacent parallel planes. The two planes are parallel to each other. So, what is the separation between these two planes is given by this relationship. D is equal to A divided by square root of h square plus k square plus l square, where h, k, l are the Miller indices of this plane, right. So, these two relations, the relation of the angle between two planes and the separation between two planes, are going to be quite important along with the atomic density of each plane in determining the properties of each particular plane, and that will tell us for any particular application what should be the crystal orientation. Let us explore it a little further. You know that the separation between two planes are given by this relationship. D is A by root over h square plus k square plus l square. Therefore, if I have two 1 0 0 planes, that is this front plane and this back plane, the separation between them is simply A. You can see it from here. The separation between them is A. I can work it out for 1 0 0 planes. Agreed? For 1 1 0 planes, and for 1 1 1 planes, so from this what do we see? We see that the 1 1 1 planes are, they have the least spacing between two adjacent parallel planes. In other words, 1 1 1 planes are most closely spaced together. This is quite an important observation, the fact that 1 1 1 planes are spaced most closely together. In order to fabricate any device, you will first need to have a block of single crystal silicon. Single crystal silicon is generally grown from the melt, okay. And when you are solidifying the melt under controlled conditions, it is easiest to grow it in the 1 1 1 direction, because the 1 1 1 planes are most closely spaced together. It is easier for the crystal to grow in that direction with the least spacing between adjacent planes. It can just grow very easily in that particular direction. So, it is very simple to grow, let us not say it is very simple, it is much simpler to grow 111 crystal than if you want to grow the crystal in 100 or 110 direction. What does that mean? See, finally, as engineers, you must always realize that everything boils down to the cost. It is easier to grow silicon in 111 direction. Corollary, 111 crystals will be cheaper. That is one of the major reasons why almost all bipolar junction transistors were fabricated on 111 wafers, because they are readily available and they are cheaper. Therefore, the cost of your fabricated device can also be kept low. Finally, you will have to sell whatever integrated circuit you make, you have to sell it. Therefore, it is easier to grow and it is also cheaper. But there are other considerations which we will consider later. For certain particular applications, for example, for MOSFETs, you may not want a 111 crystal. We will consider that in a few minutes. While on the subject of this least spacing between adjacent parallel planes, let me also tell you that because of this reason, it is most difficult to etch silicon in 111 direction. Least spacing between them. Okay. Therefore, they want to stay put, it is difficult to etch them off. So, there are many chemical etchants. When silicon is subjected to those chemical etchants, it etches it selectively, that is, it will etch other planes, but it will not etch 111 planes. Therefore, when you are etching, 111 planes will be exposed. The etching will stop when it encounters an exposed 111 planes. This again has some very interesting fallouts. Look at the angle between two planes. Cos theta is given by this relationship. Okay. Now, suppose you have an 100 wafer. Okay. Suppose you have an 100 wafer. You have exposed it to a selective etchant which is going to expose the 111 planes. Now, the angle between the 100 plane on the surface and the 111 plane which you are going to expose is going to be given by this relationship. So, if you work out, cos theta will be given as u1 u2 plus v1 v2 plus w1 w2 cos theta is going to be 1 upon root 3. This works out to be an angle of 54.74 degrees approximately. 54.735 or something, 54.74 degrees. What do I mean by this? What I mean is something like this. You have the 100 wafer. This is the cross sectional diagram. Okay? You have the 100 wafer. Now, you have exposed it to the etching through a window. Let us see, you have protected this by means of oxide. and you are subjecting it to etching. So, what is going to happen? The etching is going to proceed like this. And the angle, that is this angle, is going to be 54.74 degrees. Do you realize this surface is actually my 100 plane, and this what I have exposed is 111 plane. So, this 111 plane meets the 100 plane at the surface at an angle of 54.74 degrees. So, you see there are some very interesting facts associated with this particular properties of the 100 and the 111 planes. First of all, if I keep on etching, continue the etching, finally what I am going to have is etching cannot proceed any further, it is going to stop here, and this height will be determined by the width of the window, because you see this angle is fixed. Therefore, I am governed by this window opening to know finally how much I can etch. It will be a self limiting etching. Etching will finally stop at a point, no matter how long I keep etching it. So, this is actually a very useful property of 100 wafer, and this particular thing, it has various application. Incidentally, this is called a V groove etching, right. The name is self explanatory. You are making a V groove in 100 wafer. So, this V groove etching has various interesting application. One such application is you have a device called a VMOS or a UMOS. Very briefly let me tell you what that is. For that UMOS you have a structure like this. You have etched it down and you have a structure like this. So, now this portion can be the source and the drain, and you can have your gate here. So, what have you achieved? You have achieved a MOSFET with a very small channel without actually having to have very crucial photolithography. By deciding the time of etching and by keeping this window dimension, you can actually realize a channel length which is going to be much smaller than your original window opening. So, it is used in VMOS. It can also be used in isolation between two devices. If you can etch it down, you can have one device here and the other device here. It is also used nowadays. There are a lot of interest generated in micro machining of silicon, and this selective etching is very much used for micro machining of silicon. These topics will cover later on as the course progresses, but let me tell you that this is a very interesting fact that first of all it is difficult to etch 111 planes because of its least spacing between adjacent parallel planes, and secondly it is very interesting that 100 and 111 meets each other at this particular angle of 54.74 degrees, which makes a lot of interesting possibilities. Okay. Now, 111 plane also has another interesting property. It has the highest tensile strength and modulus of elasticity. Highest tensile strength and modulus of elasticity among the other planes. So, what is the fallout of that? That means it is very hard to crack, right. Now, you see when I am making a device, I have a big disc of silicon, a big silicon wafer like this. big disc of silicon. I would like to cut pieces from here. How does one cut? Usually what is done is you scribe using a diamond tipped tool. You scribe like that and then you try to cleave it, break it along the scribe lines. So, the natural tendency of silicon will be to break along its natural cleavage plane. And what is that natural cleavage plane? Obviously 1 1 1, because 1 1 1 has the highest modulus of elasticity and the highest tensile strength. Therefore, when you cleave a silicon, the plane you expose is going to be 1 1 1. Agreed? So, 1 1 1 is the natural cleavage plane of silicon. Fine. If I have an 1 0 0 wafer, let us say that this surface is actually 1 0 0, and when I am cleaving, I am going to expose 1 1 1 planes here. The plane that I am going to expose here is actually going to be 1 1 1. Okay. You have already seen that the 1 1 1 plane is going to meet the 1 0 0 plane at the surface at this angle of 54.74 degrees. That means, it never cleaves vertically, it always cleaves at an angle of 54.74 degrees. That is one observation. The other observation is, when I am doing the scribing, I must know how to scribe, that is along which direction to scribe. Again, this formula tells me what is the line of intersection of these two planes by this UVW. These are the directions of the line, okay. And between 1 0 0 and 1 1 1, if you work it out, you will find that the direction of the line is going to be 1 1 0. That is, this along this 1 1 0 directions, the planes are going to meet. Okay. So, it is common practice to provide this direction on a silicon wafer. How does one provide this direction? Simply, see, this is otherwise a circular disc. One side we provide a flat. This flat is along the 1 1 0 direction. This simply signifies that I am going to specify one scribe line for you. So, this flat is provided on the wafer. Your first scribe line is perpendicular to this flat. These are the first two scribe lines. Perpendicular to the flat, you can scribe. Fortunately, in 1 0 0 wafer, we have an advantage, that is the 1 1 0 lines meet at a mutually perpendicular direction, and you can cut out rectangular chips from a circular wafer. All the 4 lines that I have drawn are the 4 1 1 0 directions which are meeting in mutually perpendicular direction, and therefore, we can easily cut rectangular chips. Okay. Why did I say that this is an advantage of 1 0 0 wafer? Simply because this advantage does not exist if I have, for example, an 1 1 1 wafer. What happens in an 1 1 1 wafer? Suppose you have 1 1 1 wafer. Okay. again your natural cleavage plane is going to be 1 1 1. Okay. So, the surface 1 1 1 plane must meet the bulk 1 1 1 plane. That is, when I say 1 1 1 plane, I mean a family of such planes 1 1 1 and 1 minus 1 1 or minus 1 1 1, right. Here also, if you work out that direction of the line, you will find that they meet in the direction of 1 1 0. The angle, however, is going to be different, and the angle is going to be, cos theta is going to be, if it is 1, say if I have for example 1 minus 1 and 1 and 1 1 1, this is how it is represented 1 1 bar 1. This 1 bar signifies that this is making an y intercept of minus 1. Okay. So, these two planes, if they have to cut, it will be and this angle will work out to be 70.53 degrees. Okay. So, theta is different. Notice that even here it is not really vertical, it is not 90 degrees, it is 70.53 degrees. So, whenever you cleave a silicon, you do not really have a vertical block. Okay. It is always the bulk plane that you are exposing, it is always making a non 90 degree angle with the surface. If the surface is 100, this angle is going to be 54.74 degrees. If the surface is 111, it is going to make an angle of 70.53 degrees. But the important point is, even these two planes, they are going to meet in 110 direction. And where are these 110 direction? See, I have provided a flat. Therefore, my first scribe line is going to be perpendicular to this flat. Okay. So, this is 110 direction. Where are the other two 110 direction? You know, right? It is going to be like this. Remember, the 111 plane, it is bound by the 3 110 lines, and they are constituting a triangle, and the angle between these two, any two 110 lines is not 90 degree, but 60 degrees, right. It is an isosceles, sorry, it is an equilateral triangle. So, you have a small problem here. What is that small problem? When I want to scribe silicon, I would like to get as many square or rectangular chips as possible. But in this particular case, you see, I cannot scribe in a mutually perpendicular direction. I will nevertheless try. That is, I have put my first scribe line here. So, automatically I am going to try to scribe it. The next scribe line I am going to put like this. But this is not the natural cleavage direction, right. So, it will resist, silicon will resist scribing along that line. Okay. So, what I will have is not a clean break along this line, instead I will have a zigzag cut with each zig and each zag along the 110 directions, right. So, you will find that along this direction it is breaking cleanly, because it is cleaving along a natural direction of 110. But when you try to cleave in a direction perpendicular to your first scribe line, it is not going to cleave cleanly. Instead, you are going to have a fine zigzag pattern with each line referring to this 110 or this 110 lines, right. That is what I meant, each zig and each zag corresponding to 110 directions. So, it is a bit difficult to cleave the 111 wafer in mutually perpendicular direction. If I have 110 silicon, if I have 110 silicon, it is going to be very interesting. Again you see the first point is common, when I am cleaving it is going to be 111 planes, cleavage plane is going to be 111 planes. I leave it for you to work it out, find out the angle cos theta. You will find that you have 111 planes meeting the surface 110 plane in at 90 degrees. That is, again if I refer to a cross sectional diagram, if the surface is actually 110 and if you cleave, it is going to be like this. Or if you etch, for example, if you expose it to a selective etchant, the selective etchant is going to expose 111 planes and these 111 planes are going to meet the 110 planes at the surface at 90 degrees. So, if you have 110 wafer, you can have deep vertical grooves, not the V grooves like you had in case of 100 wafer, but you are going to have deep vertical grooves. You can etch deep vertical grooves only in 110 wafers, right. So, what have we seen so far? We have seen that since 111 has the least spacing between two planes, it is easier to grow the crystal along that direction. Also, because it has the highest tensile strength, it is the natural cleavage plane for silicon, and we have seen the angle between the 111 plane thus exposed and the surface plane, whatever the surface plane may be, 100 or 110 or 111, and you have seen how the scribing is going to be done. Finally, let me tell you that there are some other processing steps like oxidation and diffusion, which will also be influenced by the properties of these individual planes. For example, the atomic density. You have noticed that the atomic density was lowest in 100 plane. Therefore, when you subject them to oxidation for the same time, for the same temperature under identical condition, you will find the oxide thickness on 111 plane is more than that on 100 planes, simply because the 111 planes have more density of silicon atoms. Therefore, it is easier for oxygen to find silicon, available silicon, and react with it. You have enough supply of oxygen. Therefore, the more number of silicon you have, the more density of silicon you have, the easier it is to grow the oxide. So, when you are subjecting your wafers for any processing, you must know what the crystal orientation is, because the oxidation thickness will depend on the crystal orientation. Let us stop here today.